delta T. Now, the first example that we are going to solve related to this is number 7, example 11.7. Okay. So, an iron bar of length of some length, so let's say this iron is brass. So L1, that is length of iron bar, is 0.1 meter. A1, that is area of the iron bar, is 0.02 meter square. That is the cross sectional area. Thermal conductivity is also given for iron, that is 79 watt per meter per Kelvin. And that of brass, length again 0.1 meter, same. Area of cross section once again the same, and thermal conductivity for brass is 109 watt per meter. Okay, so this is the information. So this is the information that we have. Now the question is the free ends of iron bar and brass bar. Free ends, that is the one that is not connected here, right? They are given at temperature 373 and temperature 273 respectively. So that would mean here the temperature is 373 Kelvin and over here the temperature is 273 Kelvin. This value is given as T1 and this value is given as T2. Okay. Obtain expressions for. So first of all we have to obtain expression. Expression, that is a formula. First we'll get a formula and then we'll put the values and get the final answer. So obtain expressions for and hence compute or calculate the temperature of the junction of two bars, that is what the temperature here, that's the first question. Okay, and then obviously there are more questions like equivalent thermal conductivity, right? So that's called K equivalent. So we have to find temperature at the junction, we have to find K equivalent, we have to find the heat current through the bar, right? So we have to find all these three. So let's begin. Okay. So first of all, we are going to calculate expressions only. We will worry about putting the values later. Okay. Substitute all these 6 values at later stage, right? So let's start with the heat current. Okay, we are going to start with the heat current. Obviously these two, if this is at higher temperature, this is at lower temperature, so heat will flow from left to right, that is from higher temperature to lower temperature. So you can clearly see that these two bars, the iron bar and the brass bar, they are in series, right? Okay, you can see there are no branches. That means these two are in series. So because they are in series, the heat current flowing through them is same, and that's going to be the heat current throughout. So for example, if the heat current in iron is, let's say, 2 watt, then it will be 2 watt in brass as well. That is throughout the whole thing, the heat current is same. That is I, let's say, which would be equal to I1 and also equal to I2. This is the central idea of this solution. Again, series, so heat current is same, right? With this concept, we'll be able to get all the answers. Okay, step by step. So first of all, let's put the value of I1. Okay, so this is the first bar and this is the second bar. Heat current for I1. We definitely have no idea about the temperature of junction at this point. We know this is T1 alright over here, but we don't know what's the temperature here, right? So let's say this is T, right? Or you could say T of the junction, right? Let's say this temperature is T at the junction where these two are joined, the temperature is T. Now clearly left side is at higher temperature, right side is at lower temperature. So as you go from left to right, the temperature is going to decrease. That's why we are going to have I1 K1 A1 by L1. okay, into delta T. Now again, delta T stands for the higher temperature minus lower temperature. So we are going to write 373 or T1 is the higher temperature and T, which is unknown, is the lower temperature. Now similarly, we are going to write down what is I2. Okay, I2, again focus on this second one. Ignore this one for the time being. So here, again the formula Ka by L. So this time 2, 2 and 2, that is K2, A2 by L2. Now here I have to write the temperature difference for this brass bar. 273 will be the lower temperature and T will be the higher temperature. Once again I told you that as you go from left to right, the temperature would be decreasing, right? So we have T minus 273 because T is the higher temperature compared to 273, or again if you want to put expressions first, you're going to write it as T2, right? Again, why did I erase that value? Because the question says first get an expression. Expression is where you don't put values, you just write symbols. And now after writing symbols, simplifying it, we can put the values. So time to simplify this, right? There's a bit of math involved here, okay? Listen to this carefully. What we have is, we want to find out what is T. We want to find out what is T, okay? But we are given that K is different, alright, but L1 is same as L2 and A1 is same as A2. So I am not going to put the values, but we can still cancel them because we are given that these lengths and these areas are equal, right? So if you do that, because lengths and areas are equal, we can cancel that. Notice I have not written I. We don't need to write I over here. So this is what we get. Now I am going to multiply this inside. So K1T1 minus K1T equals K2T minus K2T2. Okay. Then bringing terms with T, which is unknown. We want to find the temperature at the junction, right? So bringing term with T on one side, right? That's the right hand side. So K1T1, this term on this side. So K2T2 equals, on the right hand side we have K2T plus K1T. Now we'll take T common over here. So finally we'll get our answer. T equals K1T1 plus K2T2 divided by, when you take T common, you get K1 plus K2 in the bracket. So the final result is that the temperature at junction will be equal to T1 K1 plus T2 K2 upon K1 plus K2. Okay. So now what we have here is that this is the temperature at the junction obtained in expression. Right? Now what to do to get the value? Well, you just have to write K1 value, you just have to write K2 value. So once you do that, and you put T1 equal to 373 and T2 equal to 273, you will get the value of T. I'm going to leave that part for you. You do it on your own. Right? Let's move on to the next. Okay. So now the second thing that we have to find is K equivalent. Instead of that, what I'll do is first we'll find out I, because not that K equivalent is tough or anything, but it's a little different. Okay, it will not match with the flow. On the other hand, I will go with flow. Let's see. What we have here is we already have the value of I1, I2 or I. That's our answer. So to find I can just find I1. And that will be it. So I'm going to put the expression that we have got once again in the value of I1 here. I repeat, I will put the expression of T here, right? Okay, and then we will put the values. So what do we have for I1? We have K1, A1 divided by L1, and then you have a bracket. You have T1 minus T, but T is equal to K1 T1 plus K2 T2 divided by K1 plus K2. Okay, so that's the value of T. Now we'll take LCM to simplify these things out. So we get K1 A1 by L1, and you take bracket. So T1 K1 plus T1 K2 minus K1 T1 and minus plus minus K2 T divided by K1 plus K. So you can see one of the terms can get cancelled over there, right? That is this and this. Those two terms get cancelled. So we have K1 A1 by L1. Those terms cancelled, and K2 is common, right? From this one and this one, you can see K2 is common. So if we take it out, what we have is T1 minus T2, and then that divided by K1 plus K. So this is the expression of heat current that is flowing through either of these rods. Because they are in series, whether you find I1 or you find I2, the final answer is going to be same, right? Okay, so this is what we have for the expression of heat current. Once again, you can put all these values and obtain the final value, the answer, okay, in form of SI units, right? So that is this one, heat current. So we have obtained temperature at the junction, we have obtained heat current. Now it's time for K equivalent. Now you see, what is meaning of equivalent first of all? It's important to understand. Have a look here. We have these 2 points having temperature T1, T2. Now between these 2 points with these different temperatures, we have 2 rods or 2 bars here, right? We have 2 bars, Fe and brass. Those 2 bars, they are connected in series. Now equivalent means, listen to this carefully, equivalent means instead of 2, if we just put 1 bar, then it should behave in a similar way. I repeat what I have said. Instead of 2, if we just put 1, and it should behave in a similar way as far as the conduction or the heat current is concerned. So what that means is, so here is temperature 373 or T1, and here is temperature 273 or T2. So instead of the 2 separate bars, if we put just 1 bar, just 1 bar, okay, of some material, we don't know what material is that, no problem, right? But whatever this is, we have to find its K. Then this K is called K equivalent. Again, it should behave in such a way that the heat current here, that what we found over there, should be same as the heat current here, right? So what's the difference between these two? Well, nothing as far as flow of heat is concerned. I repeat what I've said. What's the difference between this system and this system? Nothing. The value of I is same, the temperature difference here is same, right? Only that instead of using 2 different materials and 2 different bars, we are just using one single, right? But it behaves in a similar way. So that's why this is called equivalent. The meaning of equivalent is behaves in a similar way, right? Okay, we have had this word equivalent recently as well, right? For example, if you remember the water equivalent, right, of a copper calorimeter. So again, equivalent means it should behave in same way as this. So I here should be same as I here. I repeat, I in this situation should be same as I in this situation. Then we say that it behaves equivalently or it behaves as equivalent. So in this situation, we have already found I for the left side. I'm just going to put that value from there. Okay, I hope you don't mind that. We don't need to find it again. Again, this one comes from here. We already have the value T1 minus T in this. So that's I. Now on the right hand side, we are going to put this I. Okay, for this material. Right, this is temperature T1 and this is temperature T2. Now this is where you have to be slightly careful. K A by L is what we are going to do. K A by L. But do you realize that here instead of K I should be writing K equivalent because this material is supposed to behave as equivalent. the area of cross section should be same. જેવું આ છે એવું આ થવું જોઈએ. That's the idea. I repeat what I said. Whatever form this takes, whatever geometry this takes, this should also have the same geometry. Otherwise, it's not called equivalent. What about length? Here, this one length was L1, the other length was L2. But we know both the lengths are same. So here, the length will actually be 2L1. Okay, the length would actually be 2L1. Why is it 2L1? Because we are simply replacing all of this by this. So, frankly, it should be L1 plus L2 first. It should be L1 plus L2. But we know that L1 and L2 are same. So, instead of writing L1 plus L2, I am writing 2L1. Okay, L1 plus L2 becomes 2L1. And then multiplied by the temperature difference. So, what's the temperature difference between this and this? Right now we are not putting values, so we are just writing T1 minus T2. Again, Ka by L into delta T. So this is the heat current for the equivalent. Right? Now we will simplify this expression. Okay, a lot of things are cancelled. L1 gets cancelled with L1. Okay, area here A1 again same as this, so A1 will get cancelled. T1 minus T2 also cancelled. Right? So ultimately what we have is that K1, K2 upon K1 plus K2. And this 2 we can multiply over here. So we get 2K1, K2 upon K1 plus K2 is equal to K equivalent. Right? So this is the expression for equivalent thermal conductivity. Again, the idea of equivalent is that things should be same. Right? It should behave in a similar way. Right? Only then it's called equivalent. So, same area, same length combined as these two. So that is L1 plus L2 or 2L1. And heat current flowing should be same in either of these cases. Right? So we get this expression. Now once again, if you want to find the value of K equivalent, you just write down these two values up here and right? So that's the whole problem. Putting the values and calculating, I'm leaving it for you. You can always approach me if you're not getting the correct answer at the end, right? So that's it for this particular problem. I'm going to wait here for 1 minute. Okay? You can note down if you want to note down the things, or you can ask me questions. Okay? I'm heading over to the computer. I would like all of you to have your roll number and full name mentioned. Okay? Any student without that is going to be removed from the class. Arkan, I don't understand what you mean by second step. Last second step. Okay, and question about 2A. Right. Okay. Yes, Dharmi, I read your question. I was just waiting for others to ask some questions, then I'll go back to you. Okay, last second step. Fine. Okay. So I'll explain the last second step 1 second. So I believe it's about this. So the main idea here is understanding equivalent. Instead of these two, even if we put this material, okay, then it should behave in a similar way. That's the idea of equivalent. I think you would have got it. Now we come to this. So in this case, with these two together, suppose heat current is I, which we have already found. Now instead of these two, if we put this, so now the heat current is I again, right? That is what is meaning of equivalent, right? Now here is where you got confused, right? I think 2L1. So why are we writing 2L1? See, it's like, let's say I give you two bodies, right? Let's say here is one body here whose temperature is 373 Kelvin, and here is one body whose temperature is 273 Kelvin. Right now I have
Yes, sir.
right now I have put two different bars over here. Okay, that startled me. If we put two different bars over here, now if you want to replace both of these by just one bar, but you are not supposed to change anything else, right? Instead of two bars, you want to put just one bar. You can't put a bar of length L1. I hope you realize that, because if you put a bar of length L1, it's not going to touch over there, right? So you definitely need to put a bar not of length L1, but actually of length L1 plus L2. Okay, so hopefully that makes everything clear, right? Okay, so that's what we have going on over here. That's why the length is not L1 but 2L. Okay. Right? Any more questions, anyone? Area should not be twice, my friend. Arey Raj, શું વિચારે? Why should area be twice? When you put these two in series, when you go from here to here, do you realize that to go from here to here you have to add the lengths, but you don't have to add the areas? Correct? When you go from here to here, the total length is L1 plus L2, but total area is not A1 plus A2, right? The area is same, it cannot be added. I hope you got that. So here in series we are getting addition of lengths but not addition of area. That would actually happen in parallel. If you'll imagine, you'll get it. Okay. Right, so let's go to the next thing now, the next question. Right? We go to the exercise. Hopefully there are a few questions like this. Right? In the exercise, we have this question number 18. Question 1-8. Okay? Question 18. Right? It's given that a brass boiler has a base area. The brass boiler has a base area of 0.15 meter square and thickness of 1 centimeter. I see that some of you have different numbers in your book. Question numbers are not the same. So just go to this question where it reads a brass boiler has a base area, right? In my book this is question number 18, but I know that some of you have different editions of the book, so it might not be same. So please go to this question, which is a brass boiler has base area 0.15. So it's given that we have a boiler whose base means lower part, has how much cross sectional area? It says this is that area. We are looking at it from the side, and that area is given to be 0.15 meters square. Okay, and thickness 1 centimeter. So the base is thick. Hopefully you understood. It's like you know, the top, the desk of your bench, if you can imagine it. This is what we have. I'll just try to draw a better diagram. Right? Let's say this is the base of that boiler. Right? Its area is 0.15 meters square, and this thickness is given. The thickness is 1 centimeter. right? It boils water at a rate of 6 kg per minute when placed on a gas stove. So let's say here below it there is gas, okay, and this is upper part of the vessel, right? And inside this vessel, what is filled? Water is filled. Hopefully the situation is clear to you. There is a vessel which we are calling the boiler, right? In that vessel, water is filled, and that is kept on a gas stove, so it is heated from bottom, right? It is heated from the bottom, so heat will flow from the gas to the water, that is heat will flow upwards. Hopefully this diagram is clear to you. The heat will flow upwards like this to the gas, to the water, right? From the gas to the water. Now it is given that it is boiling water. It is boiling water or boils water at what rate? 6 kg per minute. Means in 1 minute 6 kg of water is boiled. Right? Okay, in 1 minute 6 kg of water is boiled. This quantity you can write like this: mass vaporized. See, MV. Again, MV for mass of water vaporized per unit time. Okay, or you will write delta T also if you want. MV by delta T is equal to 6 kg per minute. Again, mass vaporized 6 kg per minute. Okay. So it boils water at this rate. Estimate the temperature of the part of flame in contact with boiler. See, there will be flame here. Flame, that is when gas burns, you know there is a flame, right? So here, when this flame touches the lower part, right? You can think of it that let's say this is the boiler, right? And here there is the lower part of that flame, of that boiler where flame touches it. So what's the temperature of that part? Estimate the temperature of the part of the flame that is in contact with the boiler, right? So basically, this is the bottom. Okay, this side view. We want to find at this point what's the temperature, right? At this point, what is the temperature? Well, we know that at the upper point the temperature is 100 degree Celsius. Now, how do I know it is 100 degree Celsius? Because above this there is water and the water is boiling, right? As I have explained, when the state is changing, the temperature will remain constant, right? And when water is boiling, the temperature definitely remains 100 degrees Celsius. So this is where the flame touches the boiler. We don't know what's the temperature. And this is the upper part where there is water, and we know the temperature is 100 degrees Celsius. We want to find what's this temperature. See, the idea is as follows. Idea to solve this question. It's that this will be very hot. So heat will flow from bottom to top, bottom to top, bottom to top. Okay, heat will flow from the bottom to top. Now, when that heat reaches the top, it will be received by water, right? So water will get that heat. Water will get that heat, and water will boil, right? Water will get that heat, and water will boil. Okay. So we know that in 1 minute 6 kg water boils. So now you can relate all these quantities, right? Okay, because the difference of temperature, it is connected with current of heat, that is flow of heat. Okay, so let's make the connection. Suppose this temperature is T, then I can say heat current. Then I can say heat current is I is equal to K A by L into delta T. I have just written the formula, now I am going to put the values. Okay, thermal conductivity, well, we can put K's value later. Okay, it's given in the question here, I can see it. Okay, it is given 109 and all that. Okay, we'll put it later, no problem. I am not really concerned about that. Area, which area? Cross sectional area. See, heat is trying to flow from top, from bottom to top. So we have to take this cross sectional area. So that cross sectional area is given in the question. It is 0.15 meters square. So here we are going to put 0.15 meters square. Right? I am writing these values so you do not get confused about it. Okay, K's value, nobody is confused about K, right? Now L. What is L generally? Absolutely. earlier when we have solved questions like this or when we have discussed the theory, we said that suppose this rod has length L and heat is flowing from this way to that way. So do you agree that here L actually should stand for the distance between higher temperature point and lower temperature point? Say yes or no in the chat box, I am waiting for you. Again, this L should stand for the distance where the temperature is higher and between the 2 points where the temperature is higher and the temperature is lower. Again, it's the distance from the higher temperature to the lower temperature. Say yes or no please. Okay, that's clear, right? So L here is the distance between higher temperature and lower temperature point. So this is T that is thickness. In this case, this L is actually T because heat will flow from higher temperature to lower temperature like this. So here instead of L I should be writing thickness, that is 1 centimeter. So 1 centimeter converted to meter. Okay. So this is Ka by L. Now time for delta T, which is not that tough. Right? I'm erasing this part. Okay. So what is delta T now? That's easy to do. Delta T, higher temperature minus lower temperature, so simply T minus 100, right? Why did I put these values? Because I just want you to be clear about what are the values. Okay, so this is I. Now we still don't know T, but we have a good idea about I. If you are talking about steady state, then the value of I will always remain constant. Steady state, where things remain the same. Okay, so the value of I can be written as Q upon delta T, that is rate of flow of heat. Okay, so that is heat flowing per unit time. So instead of writing dQ by dt, I can also write Q by delta T in steady state. And what is Q by delta T? Here this heat is received by water. The heat is received by water, the water boils. So instead of writing Q, when it's boiling water, I can write mV into LV, right? Hopefully you remember, latent heat of vaporization. Whenever a fluid is boiling, you can write that heat is equal to m into L, right? Okay, so why did I convert it to that? Because we already have a value of this thing, right? So once I put I's value as this here, I'll just put both of these together. So that will be our next step. That will give me mV LV by delta T, right? mV LV by delta T is heat current. Now that heat current is equal to this. Okay. So what shall we do now? We have value of mV by delta T. We can write 6 kg per minute. Be careful about the units. Okay, this is per minute. So if I want to convert to per second, then I'll have to divide by 60. Again, this minute to be converted to second. So we get 60 here in the denominator. Into LV, I believe LV would be given in the question. Latent heat of vaporization. Yes, it is 2256 into 10 raised to 3. Okay, in my book there is a mistake. Let me just confirm. I think this value is wrong. Okay, let me just confirm with the table given in in the text here. Latent heat of vaporization 22.6 into 10 raised to 5. Okay, no problem. 22.6 into 10 raised to 5. Yeah, fine, no problem. It's correct. Don't worry. It's okay. So 22.6 into 10 raised to 5. Okay, we can use the exact value given in this 2256. 2256 into 10 raised to 3. The value is right. Don't worry about it. Okay, I was just a little suspicious. That's it. Now we put K's value, thermal conductivity of this brass boiler 109 in SI units. You can see it is in SI, so don't worry about converting. 0.15 on 10 raised to minus 2 and then multiplied by T minus 100. That's the next step. Okay, so now you have to do the calculations and you will get the answer. Again, in this question we connected two concepts. One, boiling of water, that is latent heat and all that, you can see that here. And the other, we related with heat current so that we can find this temperature. So we got hold of two concepts. One is latent heat and the other is heat current. Okay, if you have questions, you can ask me now. Otherwise, we'll go to the next one. Any questions, anyone? Okay, no questions, I believe. Right, no questions. So let's go to the next thing. There is a similar question, and that question is 17 from the exercise, means previous question. In my book, it's just the previous question to this one. Okay, so let's do that. Right? You can start reading the question. Well, here we are. The question is, a thermocol ice box is a cheap and efficient method for storing small quantities of cooked food in summer in particular. So if you could not find the question by the number, it reads as follows: a thermocol ice box. Okay. So what does it say? So we are talking about an ice box. I don't know whether you might have seen an ice box, but it's like the shape of a cuboid. Okay, it's typically of the shape of cuboid like this, and there's a lid. You can open it, close it, and you can put whatever you want inside. Okay. A cubical ice box of side 30 centimeter. So what is its side? Side length is 30 centimeter. 30 centimeter. It's a cube, right? It is a cube. Has a thickness of 5 centimeter. I repeat, it has a thickness of 5 centimeter, right? I'm sure you have seen thermocol, right? It comes in various thicknesses. So here it is given that this thermocol box, okay, it is having a thickness. I'm trying my best to draw a diagram. Okay, you can laugh if you want. Okay, this thermocol box has 5 centimeter thickness. So if you look at one wall, let's say the left wall, then the left wall would look like this, with this thickness being 5 centimeter, and the thickness between one wall and the next wall here, this is given to be 30 centimeter. Okay, right? Now the question is, if 4 kg of ice is put inside this, so let's say here we put ice. Okay, the mass of ice is 4 kg. Estimate the amount of ice remaining after 6 hours, right? So the question is, you have to find out that if you put ice in it and close it from every side, then how much ice will remain? How much ice remains after 6 hours, right? So instead we are going to do opposite. We will find out how much ice melts in 6 hours. Because for that we can use a simple formula. See, if you find out how much heat is transferred, listen to this carefully. We will find out how much ice melts. So if you find out how much heat is transferred from outside to inside, obviously in summer the outside is very hot, so heat will come inside from all directions. Okay, so Q equal to ml. So if you find heat transferred from outside to inside, we will be able to find m, that is mass of ice that melts. I repeat what I have said. If we find out how much heat flows from outside to inside, then that's Q. And by putting the value of Q, we can find out how much mass m melts. So, whatever melts, okay, the remaining we can find by subtracting from total. Okay, so total minus whatever melts, that is going to give us how much remains. So that's the plan. Okay, here of course we'll have to use latent heat of fusion. So first of all, we'll find out how much heat is transferred. So you see, it's a similar question. In the previous one, the boiler question, we had heat was flowing and the heat was boiling water. Now over here, heat is flowing and heat is going to melt this ice. Okay, right? So Q, how much heat flows in 6 hours? That's the first thing to answer. How much heat will flow in 6 hours? So let's think about it. You see, heat can actually flow from any of the 6 sides. Okay, heat can flow from any of the 6 sides. Right? A cube has 6 faces. Correct? Right? Left, right, up, down, and front and back. So that way it has 6 faces. Right? Or 6. Yeah, let me just write 6 faces. That would be better. And you see, all the 6 faces, they are going to be in parallel. You might not be ready with that so easily, you might not agree to that, don't worry. If you don't understand that they are in parallel, no problem. I have another way. It's that you can think that if we find how much heat flows for one face, and if we multiply that by 6, do you agree that we'll get the answer, right? For one face, whatever heat flows, if we multiply it by 6, because heat is actually going to flow from all the 6 faces, right? So this is our plan. Okay, instead of worrying about being in parallel, which would give the same result, no problem, but Q for one face and then multiply it by 6. So let's find out Q for one face. Now I'm going to do it as follows, that because here while ice melts, the temperature shall remain constant, that is 0 degrees Celsius. Okay, so temperature 0 degrees Celsius and ice is going to melt, so temperature won't change. Now what's the outside temperature? I believe that would be given in the question. Yes, it is 45 degrees Celsius. So outside temperature in every direction is of course 45 degrees Celsius. So let's say you want to find out how much heat flows through any one of the walls, like for example the left wall. So heat will flow from outside to inside, from 45 to 0. Again, from outside to inside, that is from 45 degrees Celsius to inside, which is 0 degrees Celsius. So heat current for one wall is as follows. Again, Ka by L into delta T. Now we are going to put values in the formula. K for thermocol. Okay, it is given as 0.01 in SI unit, joule per second per meter per Kelvin or watt per meter per Kelvin. So this is 0.0 for K. Now what about area? Again, it's like a wall. So here you are seeing this area. So the face area, remember this is the face. Face area of a cuboid. Remember cuboid, again L each side, isn't it? So one face area is L into L, that is L square. So here I am going to write L square. Okay, where L is the side length of cuboid, that L is nothing but 30 centimeter. So let me just put that 30 centimeter here. So 30 is 0.3 meter square. Again, it's a cuboid. So the face area on the left face is L square, but the side length or the edge length of the cube is given as 30 centimeter or 0.3. So the area is 0.3 square divided by length L. Now what is L? Like we had in the previous question, L means the distance between the 2 points with higher and lower temperature. So higher 45 here, lower 0 over there. So the distance is this thickness, again like it was in previous question. So instead of L, we are supposed to write this thickness. So that thickness is 5 centimeter, that is 5 into 10 raised to minus 2. Right? right? So that's the value of F. Now delta T is very simple, it's 45. So this will give you the heat current of one phase. So if I want to find how much heat is flowing through one phase, so heat flowing through one phase in 6 hours. Don't forget, the time is 6 hours. So we want to find how much heat is flowing in 6 hours. So we can say Q for one phase is equal to I into delta T. Again we are using the steady state idea. This temperature constant, outside temperature constant, so steady state. So I equal to Q by delta T and delta T multiplied over there. So Q equal to I delta T. So that's going to give us I, that is all this. I'm going to leave it like that. Okay. And then delta small t. This small delta T, don't forget, it's not time interval. Sorry, it's not temperature difference, it is time interval. That is 6 hours. I repeat, this delta small t is nothing but time interval. It's not temperature difference. They are not the same. So 6 hours, I into 6 hours. 1 hour is 3600 seconds. So 6 hours is 6 into 3600. This is just Q for one phase. We still have 2 steps to go. So total heat given to ice. Okay. The next step is total heat given to ice. So for one phase we have found it. Now we are going to multiply by 6. So this is equal to Q, which is 6 times Q of one phase. And this Q is going to cause the melting of ice. Okay. So that means I can write M into LF equal to 6Q into one phase. You can put all these values, of course, right? Okay, at the moment I'm not calculating this, otherwise we could definitely do it, right? So you can, when you start, you find this and then you put the value of I and then you put the value of Q of one phase and all that. So this will give you mass M, right? This is going to give you the mass M that melts. So final answer, I'm just writing the final answer as we will get it here. The final answer will be 4 kg total ice. From that, whatever melts, we subtract. So this is the remaining ice. Okay, so that's going to be your final answer in kg. Don't forget, right? So that's it for this question. Okay, I'm just going to wait over here for 2 minutes if you have any doubts.